In order to solve this equation, we're going to use techniques specific to homogeneous equations. How do we know this is a first-order homogeneous equation? Well, there's a test for this. So homogeneous equations can appear either in this form, where we have y prime solved for a function of both x and y, or it can appear in the form m dx plus n dy equals 0. Now, exact equations can also appear in that form, so how do we tell them apart? The test is to replace x with tx and y with ty. If we can make this replacement and the t will cancel out in this form of the equation, or it can be factored out in the m dx plus n dy form of the equation, then that will prove that we can use the substitution technique appropriate to homogeneous equations. So we're going to go ahead and test this. Now the dy dx we don't have to worry about. So we have dy dx, and on this side of the equation, y will get replaced with ty, and then the tx and ty, and then in the denominator, x squared becomes tx quantity squared, or t squared x squared. Now we can see that if we can factor out the t here and the t from this parentheses, we're going to get t squared y x minus y over t squared x squared. And so now we can cancel out the t squareds, and that will give us the original problem we had to start with. And so therefore we can prove that this is a homogeneous equation, and in particular, since we canceled out the t squareds, then this is a homogeneous equation of order 2. That's not very important to us right now what the order is, but that is what it would be. In an m dx plus n dy version of the equation, the t squared would be able to be factored out. Okay, so now that we've established this is homogeneous, how do we solve it? So the substitution we're going to make is that y is equal to vx. So v is some function of x, but it has a common factor of x that we can factor out. Now, in order to make our full substitution, we're also going to need the derivative of y. And so because v is a function of x, we're going to need the product rule. So y prime, so dy dx, is going to become v prime x plus v x prime, but the derivative of x with respect to itself is 1. And then the next thing that we're going to need later on in the equation is solving for v in terms of y so that we can put it back into the yx form of the equation once we're finished. Now you will see some methods for solving homogeneous equations where they tell you to write the original equation in terms of y over x. That's just another way of making the substitution. I find this method a little easier though. All right, so on the left side of the equation, we're going to substitute our v prime x plus v for our y prime on this side of the equation. And on the other side of the equation, we're going to make our substitution on that side. So y becomes vx, and then in our parentheses, we have x minus vx. And then in the denominator, we just have our x squared. Now, we're going to factor out our x's in the top. And so we're going to get v x squared 1 minus v. And on the bottom, we still have our x squared. And now we're going to cancel our x squareds. And we're going to get v 1 minus v. Or, if you prefer, v minus v squared. All right, so that leaves us with v prime x plus v equals v minus v squared. Now, what do we do from here? Well, we're going to add this stray v right here to the other side of the equation. Subtract it, in this case. And if I subtract v from both sides, the v's are going to cancel out. And I'm just going to get v prime x is equal to negative v squared. And then we have an equation that's only in terms of v and x, and it's separable. So I'm going to separate, put the v's on one side of the equation, and put the x on the other. And so remember that v prime x is dv dx. We took the derivative with respect to v. And so what I'm really doing is I'm going to divide by x, so multiply by 1 over x, and then multiply by dx, and I'm going to divide by v squared. So if I do all that, I'm going to get dv over v squared is equal to negative 1 over x dx. Now, you certainly can, if you want, keep the negative with the v squared. That will simplify the derivative in this case a little bit easier. But that's not necessarily always the case. Now, what's the antiderivative of, let's rewrite this, the antiderivative of negative v to the negative 2 dv? Right, so we're going to integrate negative v to the negative 2 dv, and then we're going to integrate 1 over x dx. Well, using the power rule, we're going to get 1 over v dv, 1 over v on the side of the equation. And on the other side of the equation, we're going to get ln x. And then we have our constant of integration. And then finally, to simplify, we're going to replace v with our original thing that we solved for up here, which was v equals y over x. 1 over v is the reciprocal, so this is going to be x over y is equal to ln x plus c. Now, this function is implicit. It's certainly possible in this particular example to go ahead and solve for y. We'd take the reciprocal of both sides. Y over x is equal to 1 over ln x plus c. And then multiply both sides by x. Y equals x over ln x plus c. But sometimes you will get solutions to these equations that can't easily be solved, certainly not this easily, for y explicitly. You may in fact get, especially if you end up doing partial fractions or something like that, you may in fact end up with an explicit solution or an implicit solution, which is perfectly fine.